Welcome. Thanks for joining. This is Switchboard's VRF workshop. If you don't know Switchboard, we're general purpose data feeds on Solana. So we power a lot of Solana DeFi. We also have like more interesting use cases where we can also do like sport betting and that kind of thing. Like we're more general purpose data feeds on chain, but today we're going to focus on verifiable randomness. So yep, we're a customizable Oracle protocol for general purpose data feeds and verifiable randomness. Just touched on that. So what is true randomness? True randomness doesn't totally exist with computers, especially blockchains. True randomness is kind of hard to actually describe. Think of it like nature. Nature is truly random. Computers abide by certain rules we give them, so they can't be random. So I might use the term randomness a lot throughout. Just know it's actually pseudo randomness, just semantics. A good example of true randomness would be like a casino. You know, you're at the craps table, you throw a dice. Um, yeah, there's no one that's there that can like predict the outcome of that. So how do computers sometimes do it? They can use like special hardware like atmospheric noise sensors to kind of measure the ambient temperature in the room or something like that. It's definitely possible on other platforms, but on blockchains, it's very contained. Everything has to be open and verifiable, so you can't really have true randomness. So verifiable randomness is the solution to this. Yep, that's pretty much what I just said. All right, so what is verifiable randomness? I like to think about it like an algebraic equation. So on both sides of the equation, we have this seed, this alpha seed. That's known by both parties ahead of time before the proof. So what do we use as the seed? We use the recent block hash and the VRF account's public key. So what that means is when someone requests randomness, this seed gets generated. It says, all right, this VRF just requested randomness. Here's the most recent block hash from the validator. So the Oracle has no upfront knowledge of what this seed is going to be ahead of time. But there is one attack vector. If that Oracle was also the Solana slot leader at the time, it could rearrange transactions and kind of influence that block hash. And now it has all the pieces it needs to kind of cheat your randomness program. So that's the main attack vector. We're working on ways to mitigate this. Recent block cache is being deprecated, so we'll probably move to a new seed. I think I don't want to give specifics, but yeah, we are aware that it is deprecated and are planning on moving. So yeah, that's like the main attack vector. If the Oracle knows the block hash, it can kind of influence it. So yeah, verifiable randomness is like an algebraic equation. On one side, on both sides, we have the seed. And then for the Oracle, it uses its secret key. So only the Oracle should ever know its secret key. If that gets leaked, there's bigger issues. So the Oracle posts a proof on chain using just the secret key to derive this proof. Yeah, maybe I touch on it in some other slides. Yeah, this might be good. So the Oracle posts the proof on chain using its secret key, and then we need to prove that the Oracle calculated the correct value without ever knowing the Oracle's secret key. And we can do that by just knowing the Oracle's public key. And that is what the VRF verify is. So this all happens on chain. The Oracle will respond on chain with the proof, and then it also responds on chain with all the verify instructions, but it doesn't have to. So once the proof is on chain, you can go and call verify yourself. You can submit these 276 transactions. You probably won't ever need to because the Oracle is always going to be quicker than you. When it sends the proof, it packs like 40 to 50 transactions and sends them all at once using nonce accounts so they don't expire. So it's kind of all seamless. But yeah, back to that. So VRF proof on chain using the public key, we can kind of prove that the Oracle didn't cheat and derive the correct output. So on chain, once the proof is submitted, then we submit all the verify instructions. We get some result. That result says like, all right, the Oracle calculated the correct value, and here's 32 bytes of randomness we produced. So some of the questions we've gotten is how can you verify this yourself? You could find the Rust ECVRF package and then input the Oracle's public key and the proof and kind of generate it, but you won't really ever need to. It's all kind of happening on chain. So as that proof gets verified, we flip a status in there that says verified successfully or verified failed. So that's kind of how you know. So the verification is all on chain, and that's what makes this so secure. Is there's no way to cheat it. The program has all the logic contained. And then once that proof kind of outputs a value, it's successful. The Oracle didn't cheat. The Oracle, or rather the Switchboard program, really does a callback into your program, and that could be whatever you configure it to be. So for our example today, that callback is going to be a consume randomness instruction, and it'll just kind of take that VRF value and convert it to a U128 or U64 or something like that. Because yeah, it's going to output just 32 bytes, which isn't totally usable, but you can transmute it to whatever you need it to be. And this is kind of the full flow here. So your client here is going to request randomness from a VRF, from its owned VRF account. So each client should have its own unique VRF account. And when you create that VRF account, you define the callback, and the callback cannot ever be changed. So it's a static callback. And then every time you request randomness, each VRF account belongs to a switchboard queue. Think of a switchboard queue like a partition network. Each queue has its own set of oracles, its own set of rules that it enforces. So they're all kind of unique environments. So each VRF account each VRF account does belong to a single queue. So when working with VRF, you should pay attention to what queue you're kind of working with, because it kind of influences the security model. So yeah, queue assigns oracles to your request. It's just a round robin kind of thing. Right now, it's a single oracle assigned to a VRF request. That could be expanded to up to 8 for just more security. So yep, the oracle has no reference to the seed ahead of time unless it's the slot leader. That's the one caveat. And that's not really a Solana or Switchboard thing. That's a proof of stake kind of risk vector there. You'll probably see that with other VRFs, which like Ethereum switches to proof of stake, they'll have the same kind of issue there as well. With proof of work, it's a lot harder to modify the block hash because it's getting into too deep of details, but with proof of stake, it's easier to kind of influence that result. So the requester doesn't know the randomness until the oracle provides a response. And then once the requester can verify randomness to ensure the validity of it, but a lot of that happens on chain. And yeah, so the VRF demo is a little complicated for today, so we're gonna just go through a more simple example. We'll probably come back to it at the end if we have time. And yeah, so let's check out the VRF walkthrough demo. So some of the feedback we got was our examples are kind of hard to step through. Like we can't really do this in a single instruction. There's a lot of handoffs, like when you request randomness, the oracle gets assigned, and then you're kind of just sitting there waiting for the oracle to fulfill it. It takes about like 5 to 10 seconds. So yeah, so we think this example will be a little bit easier to explain. So yeah, let's start. I kind of touched on all this, so I don't really want to repeat it, but here is how our client program we're going to build today looks like. So very basic. We're going to initialize a state account to hold the result. Each state, you can initialize multiple state accounts in this program. The only thing is you need a unique VRF account for each one. So then we'll request randomness from our oracle. Once verified, our program will call the consume randomness instruction, which will then update our client state. So we're going to derive our VRF client key, and we're going to use PDAs for this. And the reason for it is the program can now sign for the request randomness instructions for us. And that just allows us to do more validation up front. So you can say like, have this user requested randomness in the last 5 minutes, or you're developing some game and you need randomness. Is the user supposed to be generating randomness? So you can do a lot of checks there before requesting randomness for protection. So yeah, the client state will be a PDA using the Switchboard VRF account as the part of the seed. We're going to invoke the init client to create the account. Then we're going to call request randomness. The Oracle watches fulfills the randomness, and then calls our consume randomness instruction. So pretty basic. So yeah, I didn't want to do like a live coding demo. I think this is a little bit better. Plus, you don't have to watch me type. But each step of the way in this repo, you can kind of just do git checkout and view the repo at that step. So we're going to call it VRF client, anchor init, remove some directories we don't need. And if you're not familiar with Anchor, Anchor has this declare ID macro that gets embedded in your program. And if that program ID doesn't match the key pair you use to build the program or deploy the program, you're going to have issues. I can't remember the exact one, some kind of signing issue. So what we're going to need to do is build the program so we can generate that target directory with our deploy key pair for us. Just being lazy. And then we'll get the pub key from that. And then we're going to go update anchor toml and librs. Pretty easy. No point showing that. Going to add some dependencies here. Pretty straightforward. One thing to point out is the Switchboard v2 crate. We recently added this devnet feature flag, and that means if you want to deploy this on mainnet, you'll need to remove that flag. And the reason for that is we use Anchor's account loader, and that's going to do some validation on our accounts, such as checking the account owner. And we use different program IDs on devnet and mainnet, so we kind of need that feature flag there to handle that. If you were trying to load a mainnet account on a devnet, you would have a program ID owner mismatch from the account loader struct. And that's just really seamless. Anchor's awesome. And yeah, it's just some npm dependencies. We're going to use the Switchboard v2 CLI to generate some local net environment. And then Anchor client gen is optional. I just think it's really cool and really helpful, especially as you're learning Solana. This will look at your Anchor IDL, which is the little JSON file that gets outputted with all your account instructions and that sort of thing. It's like your program schema. So Anchor client gen will read your schema and generate like a mini API for you. Really helpful. All right, now we're just going to kind of set up the folder structure so we can kind of see what this is going to look like. If you've used any of our examples before, it's going to look really similar. We use this actions folder to hold all our instructions, and then each instruction gets its own action, and then that gets all bubbled up to this librs file at the top that just executes all these actions. Each action is going to have a validate function, and that's going to do any kind of upfront logic. So I like to think of the validate as like you don't load any accounts as mutable. You're just checking all these fields. Should they be requesting randomness? Is the counter correct? That sort of thing. And if not, you throw an error and the instruction fails. And then the actuate is what like the bulk of the logic is. That's what you typically think of with an instruction. And yep, so here it gets bubbled up to librs. We're going to use pub use here for the crate imports so we can use them globally. That's pretty standard Rust stuff. And then because we're using this use crate here, we can kind of grab all those imports as well. Simplifies things. And here's the first instruction, this init client. It's going to call the actuate. Cool, pretty straightforward. Just cleaning up our anchor test here. I like to keep the pair key pair up here. It's just a little quicker whenever I need it. Yeah, more preference than anything. And then we're just going to test it works. And yeah, so that one's very basic. It's just an empty action to kind of test our structure of our program. All right, so one of the hardest things I had getting started when I was doing this was learning how to use the Solana local net validator. I think it's really helpful. It's a lot quicker when you're doing tests. Using DevNet for everything can slow you down a lot. So this will hopefully help you out. So last night I added this command to the CLI. So if there's any bugs, it's expected. I'll work through them in the next few days, but it's been pretty stable for me for now. So this command isn't new. So this SBV2 localnet env, we're going to create our own DevNet environment for Switchboard. And the reason why we're doing it on DevNet is because Solana lets us copy accounts onto our local net validator when we start. So this just kind of gives us an environment we can use as our like sandbox to copy from. So we're going to create a whole new Oracle queue network for ourselves with ourselves as the authority so we can make any changes. And it's going to generate some files here. Just to touch on some, this start local validator, if you don't want to use the anchor hooks, this just starts the local validator with all the Switchboard accounts, the Switchboard program, Switchboard IDL, etc., already copied onto the local cluster, so you don't have to worry about that. Because remember, when you start a local cluster, it's going to be completely empty. There's no programs you need to interact with, so you need to bring them all on yourself. Start Oracle, just that starts a Switchboard Oracle using this Oracle key it generated and the key pair you provided. Docker Compose is just the Docker file for the Oracle, and this anchor toml is just a file that has all the anchor syntax of the accounts you have to copy. And then, yeah, so this is the command that's due, this sbv2 anchor test. What this is going to do is it's going to look in your local directory, and if it sees like a switchboard.env or a switchboard .switchboard directory, which is what we used here, it'll load that Oracle key and it'll start up a local net Oracle for you already. And one issue we have, or I wouldn't say issue, but the Switchboard local net Oracle is just going to constantly reboot until it sees that local net cluster come online. So we're going to start the Oracle before the validator gets started. The Oracle is going to say, all right, let's connect to this RPC. Oh, not found, reboot. So you may see like a reboot loop to get started. But then as soon as anchor test kicks off, which is what this command does next, so it initiates anchor test, that local net validator comes up, the Switchboard Oracle will start processing its request. So this is just a really nice helper tool. Before you had to use like 2 or 3 different terminal shells to kind of run each of these separately. Now with one command, we kind of do it seamlessly. So whatever test script you have defined in your anchor toml, this will just execute it for you with the Switchboard Oracle already started. And then after that, yeah, you're going to want to go into this anchor.switchboard.toml and just copy all the accounts into your anchor file. So I'll just show what that looks like. So this is what mine generated. You might not need this top part. It might be redundant. We're going to give it 10 seconds to start. We're copying a good bit of accounts. Takes a little bit of time, so we'll just increase it a bit. And then here's all the accounts. So program ID, that's the Switchboard DevNet ID, yada, yada, yada. We copy that, and it's already in here, but that's what it looks like. So this is what your anchor toml should look like when you're done. I already updated the program ID away from the default one, and here's our test script that's going to run when we run that command. So awesome. And then, yeah, you can add that to your git ignore if you want. It's kind of optional. There's nothing sensitive in that directory. It's just a bunch of public keys. But if you have like multiple people working in a repo, you probably each want your own environment. So this is just, yeah, good practice. And then we're going to update our test. So here is what our test file is going to look like now. I added this switchboard test context here, and we can load from env here. We can give it a path where this undefined is. If you have it in like switchboard.1337 or something like that, you can give it the path there if you want. But if you have like a .switchboard directory, it's going to auto look for that automatically, so you don't have to give it anything. And then this final parameter here is we're going to preload whatever key pair you provided in this provider with 0.005 rep sol. And that's just so our tests don't fail. So each VRF request is going to cost 0.002 rep sol. So keep that in mind. You're going to need rep sol in your wallet when you do request. And yep, so we're just going to load the queue and look at the settings. By default, that local net env will create a queue with unpermissioned VRF enabled. That's just nice, so you don't have to worry about permission accounts being set. Just saves you a little bit of one step. All right, great. So got all the boring stuff out of the way. We got our environment set up, the program structure's there. Let's start doing the logic. All right, so the way our PDA is going to be derived is from this state seed here. Um, that's just a static seed, just to give it some entropy. You can make that whatever you want. And here's what our state's going to hold. We're going to hold the bump. So when you derive a PDA, it's looking for something, it's looking for a public key off the chain or off the elliptic curve. And the way it does that is it uses this bump to bump it slightly off the curve. So we're going to need that bump to kind of keep deriving the key in our program. So we'll just store it in the account. Max result, result buffer, result timestamp, all cool stuff. VRF, we're going to store the public key in our account, and that's just so we can kind of validate that the user is passing in the correct VRF account each time. So if you're not familiar with Solana, you have to specify the accounts to get passed to instructions up front. A lot of the hacks that are going to happen are from not validating accounts. So you're really going to want to validate that the accounts passed in are what you expect. And the way to do that is like to store it on the account struct. And here's some errors we're going to throw. Invalid VRF authority and max result exceeded. So because we're using a PDA to sign for our VRF request, when we create our VRF account, the authority is going to need to be set to the public key of this VRF client state account. So we're going to throw that error if not. And then we're going to add some anchor events. We're not going to do any kind of testing or integration with these events today, but I think it's good for you to kind of see them in action. Like I think it's program.add event listener. You can just listen to these events and perform a callback each time in your program. And that's kind of how our VRF flip app works. All right, and here's the init client state. So there's that state seed, and here's the VRF key. And that's what's going to derive our PDA. If we left off this VRF key, that means we would only be allowed to have one state account in this program. So we're using this VRF key to kind of enforce that for each state should have a unique VRF key. Cool, a lot of this is pretty standard anchor stuff, so I don't want to get too deep into it. Yeah, there's a lot of great resources on Anchor, so I'm going to keep it light. Here's that constraint. We're going to check that the authority is a state key. If not, throw the error. Really nice, we can do this in this account struct so it happens for us automatically. And we're going to need a payer to sign because we're creating a new account on chain. We're going to need the system program because we're creating a new account on chain as well. So we're allocating space on chain. And each time we initiate a client, we're going to give it a max result. And that's more business logic, depends on your use case, whatever you need. So yeah, we're going to validate the max result up here, and we're just going to set fields. The init state instructions are usually pretty basic. You're just kind of setting fields and validating that the fields or the parameters are expected. So not a lot going on here. And then we emit that event. All right, now we're going to have to go update our test. So we're going to add this await switchboard Oracle heartbeat here. And this is just going to check our switchboard queue. And if it doesn't have any oracles, we're going to sleep for 2 seconds. And then we're going to recheck if our oracle's there. So it's just kind of a loop. I think the timeout's 30 seconds. It's just waiting for your oracle to kind of come online because there's a slight delay between when the local validator comes up and your switchboard oracle initializes. So this is there for that. And then here's the new init client test. Let's see what's important. So we're going to load some settings from the queue here just to make sure we're creating the right permission account with the right permissions. And here's how we derive that PDA off chain. So anchor utils, public key, find program address sync. Make sure this client seed matches what's in the Rust file there. If it doesn't, you're going to derive a different key and you're going to have some signing issue when you send the transaction. And yep, so we're going to pre-generate the VRF key pair here so we can kind of use it for the PDA derivation. And then we're going to initialize the VRF account here with that key pair, with that client key, with our queue that we preloaded in our test context. And for now, we're just going to give it an empty callback. This is, we haven't made the consumer randomness instruction, so we'll get to that eventually. And every switchboard, well, I wouldn't say every. So VRF accounts, Oracle accounts, and aggregator accounts, they all need permission accounts to interact. The permission account allows the queue to kind of set and revoke permissions. And the way we kind of see that working is the switchboard queue could be potentially controlled by a DAO. And now the DAO can vote on revoking permissions or granting new people permission to the network. So it's like an access control thing, pretty standard. And if our queue requires VRF permissions, we're going to check if we even have the right key pair to set those permissions. If not, we're going to throw an error. That'll just save you some headaches later. And then we're just going to send off that instruction. So, yep, in its state, it's pretty basic. And then, yeah, so we can use this SBV2 anchor test command here to run our switchboard Oracle and anchor test at the same time. The Oracle is going to just start logging a ton of stuff. It's probably not very important to you. You can use this -s flag or --silent to kind of suppress them. And then one thing to also add is if you're on like a Mac M1 like myself, you're going to want to add like a --ARM to this test here, and that'll just start up a Docker container with your architecture. All right, now let's get to the core of it all. And yeah, once again, you can use git checkout tags here to kind of see what this looks like. I can add some git diff links in these as well, so you can kind of see the diffs between the previous and this step. All right, so now we're going to request randomness for our VRF account. Our state's a seed, or our state's a PDA, so we're going to have to use some program logic to sign for the request randomness instruction. Let's see what's important. All right, so in librs, we're just going to map a new instruction here at the top. All this is just boilerplate. Keeps your program kind of partitioned nicely. Add some error messages we're going to do. If someone tries to request randomness for a VRF account that's not ours, we're going to throw an error. Or if it's not even owned by the switchboard program, we're going to throw an error. And then we'll add an event here. So then, you know, if you have an app and some user needs randomness, you could have like a little modal pop up and say randomness requested by just watching these events. And then, yep, so add it to the mod file here so it's exported. And here's our request randomness instruction. So same sort of state seed in VRF to derive it. We're going to load the bump from our state. Very nice. So we don't have to pass it in as a parameter. And then we're going to use this has1 constraint here. And that's going to do, what that's going to do is it's going to load the state account, look at the VRF field, and that field has to match the public key of an account with the same name. So it's very important that they're the same name. And then the @ just throws that type of error if it happens, if it doesn't match. We're going to use the has1 again for the escrow. Each VRF account has a token escrow. So when you request randomness, you provide a token wallet with the request, like owned by whoever's calling the instruction, right? So in my case, it's the pair key pair in the test file. So the switchboard program is going to look in the escrow, and if there's not 0.002 wrap sol, it's going to try to transfer the difference into the VRF escrow each time. So if you have funds already in the escrow, you don't have to worry about the transfer at all, just transfer 0. Then we have to pass in a lot of switchboard accounts here. And this is all used by the CPI, the cross-program invocation into switchboard. So we need the Oracle queue because the queue is going to do the Oracle assignment. So we have to kind of validate that request. We need the queue authority to validate the permission account is the correct one. So just a lot of validation stuff here. I would say this isn't too important. It's just important to know all the ones you need to pass. But I mean, a lot of this is just you'd come in here and copy and paste it into your own program and then make sure you're passing the right ones. So here's that account loader thing. That's an anchor lang trait. And here's our Oracle Q account data. We imported that in librs, so we don't need to import it into this instruction. And what this is going to do is it's going to check that this account info has the correct program ID, which is the Switchboard DevNet PID, and then it's going to check the discriminator. And if you're not familiar with Anchor, it's going to add 8 bytes to the front of all the data in the account. And that 8 bytes is a hash of the account name. So Oracle Q account data gets hashed, comes up with this unique 8 bytes, puts it in the front of the account. And it does that for all of these. So this one would be permission account data, hashes 8 bytes in the front, that sort of thing. So account loader is going to do a lot of account validation for us. So definitely recommend using this in your programs. All right, not too important. Here's our pair wallet. This is a token account. We're going to check that the token mint is the same as the VRF escrows mint. You can't like transfer tokens that aren't of the same mint, so we need to kind of validate that first. And here's the authority for that token account that's going to let us send those tokens, and that is going to need to be a signer so we can kind of authorize that transfer. And like we mentioned earlier, so recent block hashes, we use that to kind of derive the alpha seed for the VRF proof. So we need to pass that in as an account as well. Any kind of account you're touching on Solana, you have to pass into the instruction to kind of access it. So make sure you do that. Permission bump and switchboard state bump, that is used by the switchboard CPI. Something we could have done is we could have passed these into the init state and stored them on that account as well. That might have been smarter, actually. That way we don't have to keep passing these in every time. We can kind of just load them from the state directly. So something to think about in your own programs. That way, this request randomness, you would need no parameters to it. You just kind of request whenever you need it. All right. So obviously, this program is very bare bones. You should have some kind of validation here. A good one to check would be when the last time a VRF was requested. You don't want to keep spamming it. Another one is we keep track of a counter for each VRF. So anytime a VRF request is successful, it's going to increment a counter. So what you could do on your program is in each client state, you could track that counter and you can kind of check that the VRF result you're seeing corresponds to the counter you expect. That's a really good check I recommend. We do that in VRF flip repo, but yeah, for here, I wanted to keep this as simple as possible. Then you could also be checking the status. I guess it's a good time to check out the VRF account. So this is what the VRF account data is going to look like. We have the status field. There's that counter, the authority that's going to approve VRF requests, our Oracle Q, our escrow, or callback. We've kind of touched on all that, but let's check out the status. So if you were kind of wanting to do some kind of validation, you would want to be checking that the status isn't isn't verifying or requesting. That means there's something in limbo right now waiting on the Oracle to respond. As soon as the Oracle verifies that proof, it's going to assign it status verified. And then once it invokes that callback, if it's successful, it'll set it to that. Or if the VRF proof failed, it's going to set it to that. Pretty straightforward. All right, so in our actuate here, we're going to load the state. We're going to load the bump as well and our max result. We're just using the max result for the event. It's not really needed for the request. And then we're going to build this VRF request randomness struct. And this is from the Switchboard v2 crate. So you'll need to kind of provide all these account infos for these, and that's going to be used in the CPI call. So it's kind of just a pass through here. So we're going to need the seeds for our client state. That's that static seed we had. I think it was like client seed, I think I called it. VRF key, and then the bump. And that's what's going to allow us to sign. So when you're doing a CPI with a program derived address, you need to kind of have these seeds to authorize that. So we're going to invoke signed here and pass in all these parameters. This is from the Switchboard v2 crate. And there. So we're going to zero out the result as we're waiting the next randomness result. You could store like a history of your results if you wanted. There's a lot of stuff you could do, but we're just setting the state here. And then boom, yeah, going to admit that event. So let's add a test here for this. So we're going to fetch the state. That's our client state account right now. And we're going to use that to load our VRF account. And we're going to load the VRF state. So we're just kind of going through, this is all Switchboard specific stuff here, where we're loading the account. Like we're kind of chaining the loading here. So our state stores our VRF account. Our VRF account stores our queue account. Once you have the VRF and queue, you can derive your permission account. Because our permission accounts are PDAs as well, and these are the seeds that derive them. Once we have that, we can kind of verify our permission accounts created, and then we're just going to send off this instruction here. And yeah, so make sure your accounts match the expected here. Yeah, I don't think there's much to go over. And then yeah, so you can run that SBV2 anchor test command. That's going to just execute the program. It'll request randomness. It'll probably verify successfully, but you don't have a callback defined yet, so you're not going to have any way to update your client state yet. So let's add that now. And this is the final piece. All right, so now we have our program requesting randomness, but we need to kind of have a callback defined that we can use that randomness value for. So we call that consume randomness. We're going to trigger an event if our client state ever gets updated. And like before, that's useful for front end. You want to listen to this event and update the UI. I'm going to map the instruction, and then here's what it looks like. So it's smart to try to keep your callback as simple as possible in terms of like number of accounts you're passing in. Just kind of makes it less complex. The VRF flip, I think, takes like 8 or so accounts because it's transferring tokens between things. Not a huge deal if you pass a lot in. It just kind of requires a lot more transactions to go through to make it successful because it affects the packing. So I think the VRF flip's like 56 transactions versus this one's 40, just because of the different callback size. So yeah, pretty basic here. 2 accounts. And then another thing is because our switchboard program is going to be calling this instruction, we shouldn't have any signers. The Oracle or the switchboard program is not going to be able to sign for your accounts. So there should be 0 signers on the callback. And here we go. We're going to read the VRF account. Just call this load here. That loads that VRF account data struct for us. It's handled by Anchor's account loader. Anchor's great if you're not using it. And we're going to get the result buffer. And we're going to check that the result buffer is not just all zeros. So when you request randomness, the switchboard program is going to zero out the result buffer. So this is kind of our check to see if anything ever even got updated. And yeah, so you should also probably be checking the counter as well here. Does the counter match the counter you store in your state? If not, something's wrong. So the counter is used to make sure you're looking at it the correct state of the VRF account. Now we're going to load our client state. We're going to grab our max result. And then we're also going to check if the result buffer matches the previous result buffer. If it does, like obviously we've already either updated our client state or something's going on. So here's our result buffer. We're going to use the byte muck crate. And so right now we have a slice of U8s, and the byte muck crate here is just going to kind of smash them together and give us a slice of U128s. And that'll just give us like more bits being used to kind of generate our randomness. Because before, like if we're only doing like 0 to 255, we could just use the first byte, but that seems kind of wasteful. They're giving us 32 bytes. Let's try to use as much as we can. So we're going to smash them together, get this big U128, and then we're going to take the modulus of our max result. So I think I gave it 1337. So that'll give us a number 0 to 1336. So then we're just going to add 1 here. That way it'll never be set to 0. All right, and if our result has changed, let's set some states here. So we're going to set the timestamp, the result buffer. I guess there might be a case where your result could come out to the same value twice, but it seems pretty improbable. So probably not a great check here. There's probably a better way to do this. But yeah, then we're going to emit this event here. And that's kind of it. So let's see what the tests look like. So first things first, we're going to want to come in here and update the callback using those two accounts we're passing in, the client key and the secret or the VRF account. And then we're going to use Anchor's instruction coder here. So we pass it in the IDL. The IDL tells the coder how to kind of structure, how to, it gives it like the account the instruction layout of all the fields and knows how to encode them. And then we give it the name, that consume randomness. So it checks the IDL for that instruction. And yeah, so we're passing in no params here, but just note that like it's also, this would come out to an 8-byte array because of that instruction discriminator. So even though there's no data, we still need to use this because Anchor needs that 8-byte discriminator for the instruction. If it doesn't have that, it doesn't know how to do that matching in that top level librs file. Cool. So our request randomness instruction did all the requesting. We just didn't have a way to weight the randomness. So we're going to await it with this function here, print it out, and then exit the function. And all this await callback is doing is it opens a WebSocket and watches the, which one is it watching? The VRF client. So it's going to watch the client and see if its state ever gets updated. Another thing we could have done is we could have watched that Anchor event directly. If the VRF client updated event ever fired, then we could also resolve this callback that way. So there's different ways to do it. So we're going to decode the client each time from its account info, check if the result's not 0. If it is not 0, we're going to return the promise. And all this promise with timeout does is just, it's just a promise with a race condition with a timeout that's going to expire in like 20 seconds or something. So pretty basic. We're going to give it 20 seconds to kind of update that client state. If not, throw an error. If so, print the result. And that's the bulk of the program logic there. And this is what the SPv2 Anchor test might output. Obviously with that silent command, because it'll just be logging like crazy. Cool, and now, so Anchor Client Gen is super handy. If you haven't used it, definitely recommend it. So we're gonna give it the IDL and our program ID, and we're just gonna grab it each time. And it's gonna generate all these files for us. And what that allows us to do is we could just call like vrf client state.fetch, give it a connection and the pub key, and it'll fetch and decode it for us. So really handy. There's a lot more you can do with it. Yeah, it definitely helps you. All right, so we did all this on localnet. What do we got to do to get this on DevNet? So let's go into Anchor Toml, change the cluster to DevNet. And yeah, so all our test files, we were using our switchboard.env file for loading our environment. That file is our personal queue that is also on DevNet. You know, if you're doing like an official DevNet deploy, you probably don't want to be running oracles yourself. So what you can do is you can kind of set that to one of our switchboard DAO queues. This DevNet permissionless queue here, that's the pub key. And the only change you would need to do is when you're creating this VRF account, yeah, you just change the queue out for this different one here and set it. And let's see. So yeah, you can come to our docs here and kind of see a list of our queues. Here's the mainnet permissioned, and we're using the DevNet permissionless here. And that's all you got to do to get it on DevNet. So mainnet's a little different, not much. We're going to set that cluster to mainnet. here is the switchboard mainnet permissionless queue. So you would change that pub key out. And then, as mentioned earlier, you just got to remove this devnet feature, or else it's going to fail to validate any of the switchboard accounts. And that's generally it. So you created your own Solana program using pseudo randomness on chain. Awesome. One thing to keep in mind is, anytime you update consumer randomness, you're going to need to go update your callback. Make sure you're using the right is signer and is writable fields. Anchor might generate that for you. There's probably a better way to streamline it, but I would use the IDL to verify that you're using the right signer and writable fields. More resources, yep, go check out our VRF flip demo. It's great, has a lot more code, has a full API, CLI, and front end. Really good for seeing how you should be integrating VRF. This was more just like basic scaffolding, test environment setup, and that sort of thing to get you more familiar with how Switchboard kind of operates. But yeah, VRF flip, I would say, is like, this is the beginner intro level. The VRF flip would be like intermediate level. Then we got some randomness documentation, which you can find here. A lot of it you should probably know just by listening to this, same sort of stuff. And then, yeah, it kind of gives the full life cycle of the update request. So that's all I have for this walkthrough. I'm going to go check Discord. Great. All right. Hopefully I wasn't muted. Let's see if we got any questions. Do you have to register your smart contract? No, this is all permissionless. So we have this, throughout that explanation, I was saying permissionless queue for us. The permissionless queue requires no VRF special permissions. So you're free to use those for VRF accounts. Where you might need to register, like air quotes around that, if you're using like a permissioned queue, that permissioned queue would need to authorize your VRF accounts to request randomness. So the Switchboard queue is kind of meant to be its own partition network of Switchboard that you can kind of control and operate yourself if you want to run your own infrastructure. But if you want to tap into like Switchboard's existing partners that are running oracles, you can kind of lease it out from Switchboard. How do you charge for the service per request? Yeah, so each VRF request is 0.002 repsol. And the way that gets transferred is, so when you request randomness, the Switchboard program is going to verify you have the funds, and then each incremental instruction is going to transfer whatever like 0.002 divided by 277 is. It's going to transfer that amount of tokens to the whoever called the instruction. So say the Oracle responds on chain with the VRF proof and the Oracle crashes or data center goes out, something happens. Anyone is actually able to call the prove instruct or the verify instruction on chain and verify that that proof it submitted is correct. And if they do that, then they would get the escrow transfer each time. Yeah, so opening a WebSocket to listen to the callback. Yeah, so the way we were doing it was we are watching the client state account. So anytime that client state account data changed, like we would fire that callback. The other way is just to watch the anchor event. Let's see. So another way we could have done it would be like program.add event listener. What did I name it? VRF client updated, I think. Oh, I gotta put that in quotes. I'll just run this really quick. Check for other questions in the meantime. And so here is that event that got fired here. And so here's our VRF client key, our max result we're accepting, and that result buffer that got outputted. And I guess another thing I should touch on, where's that VRF key? For some reason, oh yeah, I don't include the VRF in the event itself. But yeah, so here's our VRF demo, and here's the VRF account associated with my account over there. One thing that's very handy is you can use the Switchboard v2 CLI and do like SPv2 VRF print and kind of watch it this way, or not watch it, but print it out. And here's what the current round looks like. And this would match what we just saw in that event. Or no, this is from a different account, but it would match if it was the same account. And this is the callback associated with the VRF flip over there. I don't know, this command somehow broke for me within the last few days, but I'll get it fixed. There's a way to watch the VRF account, and anytime it updates, it would kind of stream the updates here. There's some kind of timeout issue going on, so I'll fix that in the next couple days. That's kind of handy anytime you're debugging, yeah, that timeout issue. All right. So if you want to generate a number between 0 and 20, so in our program, the way we did it is when we initiated our client, we gave it this max result. So in your case, you would give it a max result of 20, or yeah, I think I would say 21 actually, because yeah, we'll do max result of 20. And then in your consume randomness instruction, what we do is we use that max result here as a modulus operator. So if we gave it 20, this will give it 0 to 19, and then we add 1. That would give you 1 through 20. So it really depends on how you're using this randomness. You could structure your app completely different. So the way we did it was each client gets its own VRF account. That doesn't have to always be true. You could have a pool of VRF accounts for your program. And so anytime a user needs randomness, you could kind of assign it to that one of the VRF accounts in the pool and kind of revolve them that way. Or you could have multiple users tied to the same VRF account and kind of do it on like a delay round based system. And that just kind of saves cost. So yeah, say like you're some multiplayer game and you want to generate some kind of items on the map. You could have like a pool of VRF accounts to do that. But then say like as the game's going on, every 5 seconds you want to generate new randomness. You could have all the users be using the same randomness there. So it really depends on how you structure it. You could also have so we return 32 bytes. You could have 32 users each using one of those bytes. There's just different ways to do it. This was just a very basic example. How to handle VRF requests by the same contract. So yeah, that kind of touches on what I was just saying because it kind of depends on how you structure your program. So this program, you could have infinite VRF accounts and they could all be going on in parallel. There's no interaction between them. But if you had some kind of pool system, you would need some way to kind of track those requests. But that would be internal to your own program. So it's kind of hard to answer. We keep a counter ID. That's the same thing as a request ID pretty much. That just gets incremented. TBD on the VRF outside Solana. More info later. So the event listener does the same thing under the hood. It's going to just listen, instead of looking at the account data, it's just going to look at program logs. That's how anchor events work. It just logs something to your program, like the logs in the instructions, if you've ever been on the Explorer page. So the anchor event's just going to parse those logs for some matching string. And when it matches the string, it's going to fire the event. So it's all WebSockets under the hood. I prefer the WebSocket method versus polling. It's just a little more immediate. All right, I don't see many more questions. Yeah, the big question we got was like, how can you verify the VRF yourself? I mean, there's a lot of VRF resources out there where you could put in the alpha and the seeds and kind of do it yourself, but you really shouldn't need to do that. The on-chain part kind of handles that. And there might be some weirdness in my modulus operator. I don't know. I'll do some more testing on that. So any more attack vectors besides the Oracle validator collusion? No, but none that we know of currently. I'll put it that way. We were very careful the way we structured this. That's kind of why we use the block hash in the VRF account. There's some security researchers out there that say proof of stake exchange shouldn't use VRF. That's kind of controversial. I don't know if I believe that. But yeah, so the main collusion is if your Oracle is also the validator. So it really comes down to what kind of queue you selected. So like our switchboard queue, switchboard itself doesn't run any validators, but some of our partners might. You could run your own switchboard queue if you were that concerned about that. But that's kind of a very niche. Haven't seen it exploited yet. Hope to not see it happen. So, it depends on how you're using the randomness. Like, if you're using randomness to like secure some kind of financial stake, and some Oracle now has some large financial incentive to cheat, it'll probably try to do that. So it really comes down to picking trustful queues. And that's kind of what the Switchboard DAO is going to try to do is we're going to have like a reputation system on our oracles. You can look at an oracle's account data and see a list of metrics. How many requests have they fulfilled? How many times have they been slashed and that sort of thing. And it kind of gives you some kind of data point of how honest they are. Yeah, I would say use a reputable queue is the best mitigation. And if you're like a completely paranoid, just use your own queue and don't be a validator. Yeah, no problem. Happy to do it. And yeah, anyone feel free to like DM me or open a ticket on Discord or anything. If you're using Switchboard, I'll check out what you're doing and see if there's better ways to do it. But yeah, this was a very rough intro. If you feel like you have a good grasp on the VRF now, I would definitely go check out the VRF Flip repo. That uses that anchor client gen client here. Yeah, there's a whole CLI and a web app. But yeah, just a little more complex, but same sort of program structure to make it easy for you. So this is like what the callback looks like in the VRF Flip. A lot of validation to make sure we're transferring tokens to the right account and people aren't passing in the wrong accounts. Account validation is the number one thing to pay attention to when working with Solana. Excuse me. So yeah, here's where we kind of do some like token transfer logic based on that VRF result. If the user won, transfer some tokens. If not, take their tokens. And then we use that anchor event. And then, yeah, so our front end is going to be like listening for this user bet settled. And anytime that fires, we log something to the console. Awesome. Well, if we don't have any more questions, appreciate any feedback on these demos. If it was useful, what we could do better, or what you want to see in the future, just let us know. We're trying to do more of these workshop demo kind of situations, and also look out for a possible AMA with the team coming up. So if you have any questions about Switchboard, where we're headed, what we're about, that'd be a good time to kind of interface with the team and yeah, just meet us. If you've ever been to any conferences and meet us, it'll probably be pretty familiar. And yeah, so I look forward to seeing everyone at Breakpoint. And if there's no other questions, yeah, that'll be it. Feel free to reach out if anything